So the next speaker is David, and he will present us FaJITa, I guess?
FaJITa.
FaJITa.
Either
Okay.
works.
Okay, so there you go.
Okay. Hey, everyone. We get to talk a little bit more about JITs, but a different aspect of it. So we're going to talk about how JITs optimize programs and how we can verify to make sure that those optimizations are correct. So Michael already gave a great introduction on some JIT background, so I'll be fast with this. But the general gist is that we have two different problems that we need to solve with JITs. They need to run fast in the first place so that they can load fast whenever we're loading a web page. We need to make sure that the time to first click for users is fast and that it's rendered fast in the first place. But we also have a lot of large applications that we want to run in JIT browsers or inside the web browser. So we want to make sure that for programs that matter for running fast, we want to make sure that we can produce fast code for them as well. So this is sort of the driving feature behind all modern web browsers, and it makes them very complicated. And complicated things are buggy, very buggy. So there's been bugs all over the place in JITs, in web browsers, in basically all parts of the engine, but bugs in the JIT can lead to full chain exploits, which can compromise user systems, and have led to some really terrifying exploits in the past where foreign governments have used exploits to compromise journalists' phones and track their behavior. So we'd like to do better. And there's been a lot of work in the web browser community to try and figure out how we can make JITs a little bit safer. There's been tons of advances in, say, architecture, the inline caches that Michael mentioned. We've been working to make bugs harder to exploit if there are bugs with things like sandboxing. We've tried to verify some small independent parts like range analysis, and there's been tons of work at fuzz testing. But all of this has been insufficient. We still find bugs. So what we'd like to do is to try and verify everything. Just having a fully verified browser would be great, but browsers are giant, very rapidly developing pieces of software, and it's a totally intractable problem as it currently stands. So we'd like to focus verification on the dangerous components, the parts that are really going to make compromises possible that attackers are going to try and exploit. And in doing so, we want to try and use domain-specific details about these components to make verification more tractable and cover as large a base of the code as we can. So for another quick overview of how JIT compilers work, JIT compilers start with whatever source code we have, and then they can either be interpreted or compiled. We're going to focus on this compilation part. So sort of the expanded version of how this works is when the JIT engine decides that JavaScript code is worth compiling, it'll get translated into some intermediate representation. This intermediate representation can then be optimized, sometimes multiple times, before eventually being lowered into assembly and executed in the browser. For web browser JITs, there's also some extra information which gets passed around, which are the call frequency and type information. And these are tools which get used to inform the browser on what kinds of optimizations we should be doing. JavaScript can also have speculative optimizations because it's a dynamic language, and we can speculate on the types that we might see in the future. So we've got this big JIT engine now, but it's intractable to verify this whole thing. So what should we look at? So people have looked at a lot of different parts in the past. There was a paper at Popple, actually, that verified the engine itself and sort of taking out some of the lowering passes in the optimizations, which is great work, would recommend it. But people keep finding new bugs. So in targeting the important components, what should we take a look at? And in thinking about this, it's useful to think about what things have been targeted in the past. So we can look at a graph of different bugs and different components and how hard these bugs are defined. This is a very approximate graph, but near the bottom are bugs that are easy to find that are just going to crash the compiler on every run. Up near the top are bugs that are very difficult to find and things that crash on only particular inputs. So then we can look at what different techniques in the past have done to find different kinds of bugs and what bugs they can find in the first place. So if we think about traditional fuzzing techniques, for instance, if we have naive fuzzing where we're just generating random inputs, this is able to test the parser pretty well, but because they're random inputs, it's having a hard time targeting some of the later parts of the engine, especially as we get into optimizations, which are only run in very select circumstances. This picture gets a little bit better if we have something like semantics-aware fuzzing, where we're able to generate programs that we know are syntactically or semantically valid, but it's still not targeting the latter parts of the engine specifically. So what we'd like to do, and what we're going to try to do with this work in FaJITA, is to try and target this part specifically. We aren't going to worry too much about the previous parts of the engine that have already been tested pretty well, and we'd like to do this in as verified a way as possible, so we can check and try and grab basically all of the bugs in this section. So in our overview, this is sort of the piece that we're going to try and focus on. So with this, we're going to introduce FaJITA, which is a translation validation tool. I'll talk a little bit about some of the domain-specific optimizations that make this problem tractable, and then what we've done to actually use FaJITA to try and find some bugs. So this is basically the setup for the problem space that we're looking at. We have some input program foo, which gets run through the optimizer and produces some new program. And we'd like to verify that both versions of the program do the same thing. Now, there's a few approaches we can take to this. We can try and verify the optimizer itself. And this is the ideal case, because we can just verify the optimizer once and be done with it. This is great if you have very static code, but the problem is that Firefox is very actively under development. The language itself is changing as JavaScript specs get updated. As Michael mentioned, the files within the engine update all the time. New optimization passes are added as new ones are phased out or new ones are needed. And we'd like to be able to do this in the real world, where developers at Firefox can actually use this tool to help make sure that the engine is bug-free. So what we're going to focus on instead is verifying that the programs before and after themselves are equivalent. So we aren't going to verify the optimizer for all cases, but rather look at it for particular programs that get passed through. And this is what FaJITA is. FaJITA is this translation validation-based verifier for JavaScript JIT optimizations. Now, FaJITa's primary method is using symbolic execution, which basically expresses the program as a series of constraints. These constraints can then be passed off to an SMT solver with some verification conditions to figure out if the programs, in our case, are equivalent before and after. So the setup for this particular case, we have our JavaScript programs, as I mentioned before. These will get compiled down to our SMT program constraints, which is just the representation of the programs. And then we have an extra set of constraints which fix the inputs for both sets of the programs and the starting memory states to be equal. Now that we have all this stuff set up, if these programs are actually equivalent, then under all circumstances, which is all these initial memory constraints, the output return values should be equal, and our resulting memory conditions should be equal. For the browser JITs in particular, there's a little bit of extra checks that we have to do, which I'll omit here. But these are related to sort of global browser state. So this is sort of the general setup. But in general, this is an intractable problem. SMT solvers have historically had a hard time with this. So we're going to talk a little bit about some optimizations that make this feasible for this particular domain. So symex has a few problems in this case. These optimizations themselves operate on MIR, which is one of the IRs inside of Firefox. And there's hundreds of these instructions. These instructions have complex semantics, which interact with weird JavaScript data types. They interact with the browser in weird ways. They interact with other languages in the form of WebAssembly. And the semantics are just difficult to specify in general because they're not written down anywhere. It's just sort of an ad hoc implementation as the specification inside the engine itself. So in order to deal with this problem, we're going to do a few optimizations. There's a bunch of them that we've implemented to make this feasible, but we're going to talk about a couple of them, which are modeling a subset of the semantics that we need rather than the entire thing, and specializing the memory model to our domain. So for the first one, approximating the most semantics, let's take a look again at our two versions of the foo function. So these two versions compile down to this corresponding MIR code, which is mostly as you would expect. You can see this get property instruction here, which performs the x.bar. But there's also some weird instructions that show up, like this nursery object instruction. And there's tons of these instructions all over the place. MIR is a very complicated language, which itself has crazy optimizations that get put in to make the browser code get compiled as fast as possible and have the eventual resulting code run as fast as possible as well. So in trying to verify this, it's useful to ask what this instruction actually does. And we know it can really only do two major things. It might modify memory in some potentially unconstrained way, and it's going to produce some value. But critically, we know that it does the same thing for all of the same inputs in the same initial memory state. So because of this, we can treat this basically as an uninterpreted function. So when we're calling into, when we're trying to set up the constraints for this, we don't actually have to implement the specific semantics for what this nursery object operation does. Instead, we can just model it as we described in the most general case possible. It produces some value and it modifies memory in some way. And in doing this, we're able to just pass this off in this very general sense and set up our usual verification conditions. And we're able to verify the program just fine. This has a bunch of benefits here. We're able to get sound approximations of these hundreds of instructions essentially for free. And it's easy to refine the semantics for these particular instructions where we actually need them to be more precise. So for instance, in the previous case, we had this constant folding operation that was done. So we can just refine the semantics for the int multiply and int add instructions here. This also has the nice benefit of allowing the SMT solver to automatically handle any reordering that happens. So reordering that happens as it decides function calls might need to be reordered for caching purposes, or if there's any code motion because of loop invariant code motion, things like that, the SMT solver is able to handle automatically. So now for our second major optimization that we've done is how to optimize the memory model for symbolic execution. So memory is historically a huge issue for symbolic execution because it's just this massive array, which SMT solvers have a hard time dealing with. The major cause here is that there's a lot of layers of indirection. If you're storing pointers in memory, suddenly you have a symbolic lookup to some symbolic value, which is then itself going to go back in and do some symbolic lookup. And you can have this arbitrarily deeply nested. So rather than doing this in just this naive way where we're treating everything in symbolically, we're going to try and take advantage of the problem structure here and try to do as much of the analysis using some traditional static analysis techniques rather than just passing everything off naively to the solver. So the memory model for JavaScript in general is, as described by Michael, sort of like this. We have some object O, which has a field bar. This object has some shape, which defines where the offsets to the actual values are stored inside this slots field. Now, critically, you might notice here that there's already 3 layers of indirection that we have, and we're just dealing with a single object. We have this random object that's located somewhere in memory. We have a pointer to a shape, which is also located somewhere in memory, which itself is storing a symbolic value, which stores another offset to some slot, which is eventually going to contain the final value that we're interested in making sure is equivalent across different programs. Now, traditionally, like I said, all of these things are going to be treated symbolically. And this is what we tried doing with our initial implementation, just doing the most naive thing possible and trying to figure out how well this works, which it does not work well. It times out after about an hour on very simple representative programs and certainly does not scale up at all. So what we're going to do instead is to try and take advantage of the problem structure, like I said, and we're able to track both the object location and the field offset statically. The object location we're able to track statically because we're only trying to compare equivalence. So we don't really care where the objects are specifically located in memory. We just want to make sure that they're in the same place. So any objects that are referring to some initial parameter or to some global object, we're able to basically replicate some sort of allocation scheme. And we're able to track without loss of generality, just placing some arbitrary constraint on them, and then making sure that they're equivalent across the 2 different programs. Similarly with our field offsets, in general, we have a problem where we don't really know where these field offsets are going to be pointing to. But we're able to take advantage of the problem structure again with the specific guard instructions. I won't go into the details of which, but we're able to make this static as well. And now the only thing that we have is these symbolic field values, which makes the verification take less than a second. So with all of these optimizations we have implemented, there's many others that I don't have time to go into. We're able to verify all of the programs in Firefox's test suite, most of which take well under a second. And because of this sort of semantic refinement technique that we have a very low false positive rate. We have a very low percentage of programs that we can't handle. And for the programs that we don't yet have precise enough semantics implemented for, our tool is able to detect known cases where this happens. So for instance, we don't have function inlining yet, but we're able to detect where this happens and have the verification tool report this as a function inlining failure, rather than just as a positive or a potential source of a bug. Okay, so we've got this giant tool now, which is able to do translation validation on specific programs, but what can we actually use it for? So the primary thing that we're using FaJITa for at this point is as a bug finding tool. And we're doing this as basically an additional test for fuzzing programs. So rather than only worrying about trying to figure out when programs crash for the programs that we fuzz, we're able to do this very advanced extra test where we're able to detect if very subtle things go wrong in the optimization pass. To do this, we're basically just collecting all versions of a function during execution, which we're able to do with another tool that we've developed, which Michael is the primary lead on, which allows us to collect runtime information as Firefox is executing and basically dump a bunch of extra information so that we can actually use this technique online. We can also use the data that we dump and collect as additional metrics to guide the fuzzing process in the first place. This has been a very active, ongoing area of research for us because existing fuzzers do not search our domain well at all. You might recall in the initial picture, we had the graph of the fuzzers and the kinds of bugs that they were able to collect, and they're just not able to target the optimization pass as well. So we haven't had success finding bugs using existing techniques like FaZILi or the tools that Firefox has developed. But we're trying and figure out better ways to search this. Right now, we're using the data that gets dumped as part of this analysis pass to try and figure out if we can guide the search a little bit better, basically fixing our starting corpus based on which ones we think are more interesting. But if anybody has ideas, this is the area that we're actively working on. So if you have ideas of how to explore the optimization passes specifically, I'm very interested. We can also use FaJITa as a tool for online eventual verification. So this is doing anything with SMT solvers is probably too slow to verify things before they get executed. But we can also use this prefect tool to try and verify programs off thread instead. So rather than worrying about trying to verify everything before it gets run, we can basically pass these off as extra jobs, which can get run whenever there's extra cycles for the CPU. And do bug finding that way. Okay, so this was FaJITa. In conclusion, we've made this big translation validation tool, and we found that large-scale real-world browser component verification is feasible by taking advantage of domain-specific optimizations. Thank you.
Okay, questions?
So I'm not sure I'm not sure what the status really is. Are you able to find at least former bugs in Firefox using your tool?
Yeah, so we've done a lot of testing to make sure it works in the first place. We were able to replicate former bugs. There was another paper, Core JIT, recently, which we're also able to replicate their results for. One of the limitations that we've been running to is that we have to have programs that actually have the optimizations done wrong to them in order to detect bugs, which is why we're looking into more interesting fuzzing techniques. But we have done a lot of testing to make sure that our tool is actually accurate and it's able to find bugs if they exist.
I see. So if I understood correctly, if you give a former program that's known to optimize wrongly,
Right.
your tool will find it. But the problem is to find these programs that optimize wrongly, right?
Yeah, exactly.
Excellent.
Yeah, so we've there's a proof of concept examples, for instance, in the Firefox test suite for where optimizations go wrong, and we're able to detect those with our tool.
Super nice. I think the idea is really cool.
Thank you.
So I'm wondering a bit about this, the bugs that you're looking for in the optimization process. Are you looking for like things, programs that, for instance, as FaJIta could figure out as like programs that are optimized incorrectly versus simply programs that crash the optimizer?
Yeah, so we're looking for any programs that get optimized incorrectly. So this is in browsers, basically anything that gets optimized wrong or diverges from the original source JavaScript semantics winds up spilling over into a full-scale or a full exploit. So anything that goes wrong is what we're looking for, basically.
Okay. So maybe if there's, I have another question. So going back to this big picture that you had at the beginning, right?
Yeah,
the
with the
effectiveness of the things. So I'm wondering why. So is the fact that finding bugs in the optimizer is difficult because it's just kind of at the end of the pipeline, and you do need to get there, or it's just that the optimizer is very kicks in just in very selective conditions, and then you don't, you're just generating a gazillion of inputs and programs that get discarded or at that point don't satisfy the condition.
Right. So it's sort of a combination of both. It's a harder space to search in general if you're using fuzzing techniques because there's only specific conditions that the engine will actually pass things off to the optimization pass. So in particular, things have to have run frequently enough. It basically has to decide that the function is worth optimizing. But it's also an unexplored space, I think, just because of the techniques that we've been using to try and find bugs here. As it stands, finding bugs in the browser basically amounts to doing a bunch of fuzz testing, as we've mentioned, or just looking through the code by hand. And there's not really many other major techniques that have been used to try and do this. There have been like static analysis tools, for instance.
Because to me, I mean, one natural way of overcoming some of the limitations to me would be just, not going through the entire pipeline, right? Just inject things straight before the optimizer, generate random things in a, slightly smarter way and see what happens.
Right. So that's something we've been thinking about more recently. One of the initial concerns with that is that there's a lot of well-formedness conditions that are placed on this MIR, which the optimizer operates on. We originally hadn't done it because I think it's probably a lot of extra work to figure out how to generate programs with this well-formedness, because you have to deal with things like the JavaScript garbage collector, for instance. But that's definitely something we're looking more into, because that's a potential good source to generate more directed programs.
Okay, cool.
Yeah.
If there's time, maybe just one idea. In a way, I mean, if there's certain complicated invariants that wouldn't, or complicated conditions that would need to be satisfied, then maybe something like symbolic execution, or like using something like symbolic execution to symbolically generate the program that takes you there. But if the conditions are just simple dynamics, you just count how many times something gets called. I mean, I guess this can also be, the optimizer can be tweaked to set this boundary very low and to allow many optimizations if it's just based on a simple dynamic counter or something.
Right. So we do have like the code that we've set up to actually reach the optimizer. We've tweaked to basically have it run to the optimizer as often as we can. One of the reasons this hasn't worked well, we think, is that a lot of bugs are because of weird interactions between speculative optimizations. And just in general, whenever there's a lot of, or there's many iterations on this optimization path that gets run, seems to be where the bugs are more common. We've thought a little bit about extending the symbolic execution side of things to the MIR side itself. I worry that that will quickly blow up the program space too much because I don't know if there's as many of these static optimization tricks that we can run on that side of things.
Okay, someone else?
So maybe.
Okay.
Sorry, just because I think it's super cool. So I was just wondering, I mean, what you could also do is, just run it a bunch of times, maybe in something like QEMU or something like this. Get the snapshots just because you got the verifier. So with valid inputs. And then you start messing up there.
Sorry, could you repeat the first part again?
So you just generate, I mean, you get a bunch of traces, right? You just run it, simulate to use something like QEMU or something like this. You take the state just before the optimizer kicks in, and you mutate that.
Yeah, that might work pretty well. There's there's a potential concern about the size of the space we're exploring at that point, because a lot of the setup is related to where objects are set up in memory and the kinds of programs that we're trying to optimize over. But that would let us at least explore the kinds of optimizations that get run a lot better, I think.
Okay. Really looking forward to see what's the next step here.
Yeah. We're hoping to publish with some results soon.
Okay, let's thanks